Perfect. Thank you, David, for the invitation and hosting me here in Spain. And also, thanks to Roy and Fabrizio, I guess, for making my life easier. Roy provided an overview. Fabrizio focused on the model, so I will talk more about the computation. So I will try to avoid repetition. About me, I'm an associate professor at Texas State University. And we started, I guess, working on this. Obviously, David and his team has been working on this more than a decade, but I probably got started maybe 6 years ago, I would say. And this work is joined with Roy and Alberto, and obviously David also has been a part of it. And standard disclaimer, recently we got an Air Force grant supporting that. So I will more talk about non-cooperative games. Again, some of the things Roy already mentioned. And the idea here is that the way at least I'm approaching this is more like a decision problem. Basically we have two decision makers. And in this setup, two decision makers happen to have different goals, and it may also end up being one of them maybe an adversarial purposes, what we call as adversary, or in the standard terminology, attacker, and the other one would be the defender. And obviously in literature, these are called as Stackelberg games, sequential defend attack games. And today I'll be focusing more on the sequential games, but obviously there are simultaneous games as well. And I will try to provide an overview and a framework. So I'll talk about games with complete information, where most of the game theory literature focuses on. And then there will be the games with incomplete information, which are more realistic, especially in cybersecurity or domains like counterterrorism, because most of the time, defender wouldn't know exactly what adversary thinks, what the probabilities and utility functions of the adversary are. And one thing, obviously, we are in an AML session. You may question how this is relevant. The main idea is that, game theory has been around for a while, right? But most of the time, because of computational challenges, we have been focusing more on small related problems. What do I mean by small? It may be a decision maker with a number of limited decision alternatives. Obviously, there are many approaches with analytical solutions. Here our focus is more on continuous and high-dimensional decision spaces, which especially arise in the context of adversarial machine learning. And I guess Roy talked about these a little bit. Let me give you an idea, starting with the very simple game. So this is an example of two-player sequential non-cooperative game, and we have complete information. And I believe Fabrizio discussed this influence diagram a little bit. But the idea is that we are assuming that defender is the first decision maker, agent, and attacker would be the second. Both defender and attacker, they would have their own utility functions, which would be a function of their own decision alternative, as well as their own, as well as the realization of the uncertainty. And they both have different beliefs about the uncertainty, which are expressed by separate probability distributions. So this is the general setup. Again, we are assuming that attacker as the second decision maker observes the decision of the defender, therefore doesn't have to know basically defender's utility function nor the perception of the uncertainty, whereas defender, in this case, this is the complete information case, defender is assumed to know how attacker perceives uncertainty, the probability distribution, as well as the utility function. So this is the main assumption. Defender is assumed to know the utilities and the probabilities of the attack. When you look at this problem, at the end of the day, it comes down to expect utility maximization, something we are very familiar with. And I guess the devil is in details, and the problem becomes more challenging when we want to explore high-dimensional cases. Because as I will show you, at the end of the day, if we can basically solve these expect utility maximization problems, we are in good shape, right? And the standard way of doing this is we utilize some sort of backwards induction. We can solve the attacker's problem, which is nothing but the solution of the summation or integration for the attacker's expect utility. We come up with an attacker's decision alternative for each defender decision alternative, which we denote as A star D, and then plug that into the defender's decision problem and solve defender's expect utility maximization problem. And this provides us the what we call as the Nash equilibrium, which has been well studied, and again, there is quite to work on this. So the question is, how do we do this, right? And my talk, as I mentioned, is going to be more focusing on the computational aspects. So expect utility maximization problem traditionally is a both estimation and the optimization problem. So we do conduct those tests in a sequential manner. So obviously, if we can compute basically first, we try to estimate the expect utility function. We do that for the attacker's problem. We generate these samples from the probability distribution, basically representing the attacker's beliefs, and then let's say that we collect a number of Monte Carlo samples, and then we plug them into our approximation. And we then solve that optimization problem, right? So this is sequential estimation, then optimization. And in some cases, it's easy to solve, life is good, and in some cases, it may not be. And we do that also for each simply defender decision alternative, and then we would get an optimal attacker decision for each decision defender decision alternative. And then eventually we will plug that into the defender's problem, and then we will be able to compute what we call as the basically game theoretic solution under complete information. Again, this is very fundamental. It's great when it works, but you may have noticed that my loops are based on both cardinality of the defender decision space as well as the attacker decision space. And that's where it can become problematic. When those are low dimensional, life is perfect. So the question we are asking in settings like AML, what if the high dimensional defender attacker decision spaces are available? We need to figure that out. Or even the randomness portion. That probability distribution we have for the uncertainty theta, sometimes it's easy to sample from, but sometimes it's not, right? Even it may be skewed when you think about it. So I may need to sample a lot to capture that skewness of the distribution. If I don't do that, you may say that I'm still gonna basically draw 1,000 samples, 10,000 samples, whatever your magical number is. It's fine, but then if you have some Monte Carlo estimation error, then that would impact the quality of your optimization output. So that's one of the common challenges with this type of sequential estimation optimization setup. So again, this is not a challenge only for these games. This is a challenge in computational decision theory at large. And there have been many ideas, as you would know. At the end of the day, we are trying to solve this maximization of expect utility function, call it utility function, objective function, as our operations research colleagues do. But for these reasons, such as this potential decision-dependent uncertainty, that's also another case where the uncertainty could depend on the previous decisions. Again, the challenge is that then you will have so many scenario trees for each defender or attacker decision alternative. And it could be ineffective in high dimensions or skip distributions as well. And sometimes the Monte Carlo estimation part is relatively easy, but the challenge is the optimization. Because, and I don't know, maybe Daniel may talk about this, but sometimes, especially in finance, the basically expect utility function may have a really ugly surface. So how do we optimize that while working with Monte Carlo sample? So those are the challenges we have, and I guess David was one of the co-authors more than 20 years ago. I guess a number of, and Concha Bielsa, I'm not sure, I saw her name in the program, she may be also around here. But they came up with this idea of augmented probability simulation. The idea is very simple and relatively simple and very elegant. The idea is that why don't we turn this expectation of maximization problem, maximization of expectation problem, into a grand simulation problem? How do we do that? By treating the decision variable as random. So normally we do the Monte Carlo simulation only on the parameter. Now we are saying that what if the basically decision variable, decision alternative in our case, is treated as random, and I'm searching for the optimal decision alternative in the joint domain. So we simply generate an artificial augmented distribution in the basically which is proportional to the expected utility, which is the standard. I have the utility function and I have the basically distribution of the uncertain variable. So I'm just generating an artificial distribution which is proportional to that utility function as well as the uncertainty of both the parameter as well as the decision variable. And I know that this is a little bit controversial, but the idea is that you can even treat that uncertainty about the decision variable as uniform, as if you don't know anything about the basically decision variable. Once you do that, the marginal distribution would be proportional to the expected utility, and hence the mode of this marginal distribution is going to be equivalent to finding the decision that provides the maximum expected utility. So again, instead of doing two steps, both simulation and optimization, we are incorporating the utility function into our grand simulation, as is the case over here. And this basic picture is not perfect, but I think it can be used to deliver the message. So I'm looking in the basically joint space of both decision variable as well as the random variable, and then simply, if I just look at the marginal distribution of the decision variable, the mode of that is going to give me the expected utility. So that's pretty much the idea, and basically we are trying to extend that to solve some non-cooperative games. Any questions? So in the last 10 years, this idea was solved to use maximum likelihood estimation problems. There are some papers in early 2000s about that. In the last 10 years, we use this to solve some decision problems, especially in the optimization, stochastic optimization domain. This is pretty much our effort to use some of these ideas to solve games. The assumption, there are not many. We just need to ensure that the artificial augmented distribution we have has a proper probability density. And ensuring that basically the utility function is positive and the choice set of decision alternatives is bounded basically enables us to do that. And there are some implementation issues. At the end of the day, we would need to basically sample from this joint and or marginal distribution, and sometimes the shape gets ugly. So as I will discuss, we will basically borrow ideas from the standard Markov chain Monte Carlo literature, and we utilize net sampling, and potentially in the future there could be other ideas implemented to do that as well. And another challenge is that this figure is relatively nice, the peak is obvious, but sometimes the peak may not be. So even there may be some local peaks. So that's something to be aware of. And in order to address that, Peter Mueller, more than 20 years ago, came up with this J copies idea, which is nothing but very similar to the simulated annual idea. So you are just transforming the utility function or the expect utility with a power transformer. So this is the general setup. Now I will discuss simply how this is used in games. But some of these ideas we kind of put them together, but really even there is an OR paper of Pincus from 1968 that talks about the basics of this very same idea. So there is some connection in literature, and let me know if you are interested. I can provide you some of the resources. So in our context, how do we do this? Again, I want to solve these games with complete information that I was solving with Monte Carlo plus optimization. So now I will be generating this artificial augmented distribution, and I need to do that twice because I have two decision problems. One is the defender's decision problem and the attacker's decision problem. So, but defender's decision problem requires optimal attacker alternative, right, for a given decision alternative. So first, I will need to focus on the attacker's decision problem. Again, I'm generating this distribution on the decision alternative A as noted here, and the random variable theta, and it will be proportional to the utility function and the basic density of the uncertain variable, so that the marginal of this would be proportional to the expect utility, and the mode of that marginal distribution would give me the optimal decision. And I can do the backward induction, just plug that into the defender's problem and solve it for the defender cells. So this is pretty much the idea. Again, we are removing the need for, I guess, optimization. And I'm not going to get into details, but the paper is available on archive. I guess the main thing to focus on here is now we remove the dependence on both attackers and defenders' decision space by using Metropolis Hastings algorithm. So it would depend on basically the number of simulations we do in each step, but especially if the cardinality of the decision spaces is large, this may provide us an advantage. And that's the whole idea. This works with both discrete and continuous setups, and I'll provide some examples. But in the overall framework, sometimes you have complete information, that's great, but sometimes it may not be robust. And we propose that you may want to check the robustness of the solution. How confident are you about the assumptions you are making on the utility function of the attacker, as well as the probability distributions of the attacker? So very simple idea, just adding some perturbation and trying to see if the expect utility changes. If it changes a lot, there may be a problem, and basically we simply try to answer that question next, which is the case of incomplete information. So again, there are a number of approaches out there. In this talk, I'll be using adversarial risk analysis that Fabrizio gave some details of. So I'm not going to get to the modeling details, but what we are trying to do here is to provide one-sided prescriptive support to one agent. And I guess the main, a little bit different aspect of adversarial risk analysis is we are using Bayesian ideas, and it means that we will, as the defender, we don't know the basically decisions of the attacker. Therefore, we will try to quantify that by using a probability distribution. And Fabrizio briefly talked about how to get that probability of attacker's decision given defender's decision. And here we are also using a very similar idea. And again, we need this assessment as the defender. how would the attacker basically make a decision given basically conditional and given decision alternative. And at the end of the day, it turns out to be this basically expect utility maximization problem, which also requires our uncertainty quantification of the attacker's decision problem. So this part becomes basically one of the fundamental parts in solving the defender's decision problem. And simply we are trying to solve the attacker's decision problem, and the assumption is that we don't know the utility function nor the probability distribution of the attack. And again, we just are suggesting that we are sampling from the respective distributions. So we are also incorporating some uncertainty on that. And this expect utility function itself is also random because of the Bayesian nature basically of the problem. And we would be computing a random optimal attacker decision alternative. And similar to the way that I described, we can use Monte Carlo, or as I will introduce, we will be using augmented probability simulation. Monte Carlo, the idea is very similar. Now, though, I need to add another step, and I need to generate these samples. Basically, first I need to figure out which utility function I'm using, which probability distribution I'm using. So I'm adding that additional layer of uncertainty. And I guess that's the main additional adversarial risk analysis. We are quantifying that uncertainty. Life is good, however, my number of samples that needs to be generated still depend on the cardinality of the decision space. If I have lots of, let's say, classified decision alternatives, as was the case in the classification example, I would need to solve this basically for that loop and all possible decision alternatives. Or if the attacker attacker's decision is continuous, and I want a certain high level precision, I may need to basically discretize it with so many decision alternatives. So that's the challenging part, and APS again, similar to the before, similar to the complete information case, help us to remove that dependence, and simply we would get required number of samples which are independent of the defenders and attackers cardinality of the decision space. So that's really the main idea. And then in our framework, we propose another level of sensitivity analysis to see if this set of our utility functions and probabilities are, I guess, reliable or precise or not. And basically from there, you can use basically another set of criteria to see basically what we get is robust. And this is the theoretical comparison. Again, standard Monte Carlo setup. If the decision spaces are large, there may be a problem. APS, especially the implementation with metropolis testing, basically removes that dependence. And again, obviously I don't have much time to get into details, but in the paper we also provided some illustration, a cybersecurity case, as well as a simple example. Here, this is a very simple, I guess, cybersecurity case. We have an agent choosing proportional resources to invest, and both defender and attacker is in the basically space of 0 to 1 continuous. It's a proportion. And I have a payoff function for the defender. Defender is trying to protect the server, and the attacker simply is trying to have the basically have a successful attack. And again, we have some assumptions which doesn't impact the generality of the results. We have a constantly discovered defender and a risk-prone attacker. And for the uncertainty of the basically success of the attack, we utilize a beta distribution. But the main idea here is that, again, I have a continuous setup, right? So to solve for this, I need to discretize it. And if let's say I'm in the 0-1 space, if my precision is relatively low, like 0.1, which means that I'm looking at defender and attacker decision alternatives such as 0, 0.1, 0.2, like all those 11 alternatives. If I do that, basically with Monte Carlo, it only takes 0.007 seconds. Life is good, right? When you try to do that with APS, it takes 0.24 seconds. Again, these are the number of the samples I need, and there are a little bit more details that I don't have time to discuss. But if I want to have a higher precision, if I only increase this precision by 10, if I'm now looking at 0, 0.01, 0.02, and such, APS basically requires 10-fold increase, which is linear to the precision, 0.24 to 2.4. Whereas look at Monte Carlo, it's almost 200-fold increase. Because remember the idea, right? For each decision alternative, I need to go and simulate those parameters. I need to solve the resulting optimization problem. And for even a higher precision, or with Monte Carlo, we even couldn't get the result. So this could be especially beneficial with problems with large and or continuous decision spaces. And here, the expect utility even wasn't challenging, but if it has a flat expect utility surfaces, again, I can use that transformation idea. So that may also be another added advantage because it kind of gives me the probability of the basically optimal probability density of the decision alternatives, which is another advantage. So this is an overview of what we did. Again, starting with the complete information case. If it's a small problem, just use Monte Carlo, right? If you have an analytical solution, just use that. That's perfect. But again, more and more we get into especially domain as adversarial machine learning. That may not be possible, especially if you are going to incorporate in complete information case. And again, we just recommend to complete the array solution with either Monte Carlo or APS, and then obviously recommend conducting the sensitivity analysis. So overall, this is, I guess, one of the first groups that extends these type of ideas to games. And in terms of computational game theory, I guess now we are solving bigger problems. I guess there is more interest in this area, and I guess there will be hopefully more methods, and there has been in the last 5 years. But overall, these methods, I mean APS, provides more smarter sampling, and you even don't integrate into information. That's also another advantage, because we can also throw those like stochastic gradient methods and such, and in some setups they are as good, if not better. So this may be an alternative in cases where it's expensive to get that. It provides reduced variance for the samples, reduced sample size, and these are some of the setups where APS can be a good alternative. Again, if MC Monte Carlo becomes inefficient and costly, maximization of the utility becomes challenging. If you have decision-dependent problems, remember where the probability density of the parameter depends on the decision alternatives, and if you have large cardinality of decision spaces. So these are some of the setups, and in our experiment for this paper, we also recognize that a practical strategy could be to combine these both methods. Because as I showed, MC kind of is pretty good to capture where the solution could be. So basically you may use MC for broad exploration, and if you want to go find exactly where the optimal decision is, and its sensitivity, APS could be a complementary tool as well. Overall, again, there is some open-ended work, of some of which we are currently working on. I guess improving these sampling methods is an ongoing challenge. There will be definitely more work. There needs to be more work because obviously working with MCMC, conversions can be a challenge sometimes. I guess the last few years we never could finish this, but we have been looking into how we can, rather than an estimate approach. Right now I'm solving APS for attacker's problem, and I'm nesting it to the defender's problem. Can I solve this as a one big chain? Could it be more efficient? So we are looking at it. I guess we need to work more on the theoretical aspects of it. Now, especially with this Air Force crimes, one of the areas we are looking into is adversarial forecasting. Again, we started with seeing what if a hidden Markov model is manipulated or is attacked. I mean, there is not as much work on standard attacks on the standard forecasting models. In the last 15 years, I guess the focus has been more on the classification. There is some work now on support vector machines and such, but that's a relatively open area. Other games and potential connections to subject domains. I guess I'm about to the end of my time. Any questions?